This 16th century woodblock shows fishermen pulling a big net load of hibernating swallows from a frozen lake. If you haven't heard about how swallows hibernate through the winter at the bottom of lakes, it's because they don't. But for thousands of years, hibernation was one of the leading theories to explain where birds went between fall and spring. Another theory was that birds left entirely and flew away for the winter. We called this migration. But people didn't have a clue where the birds would go. For example, a pamphlet from 1703 suggested that they went to the moon. The first real clues about where migratory birds actually go during the winter, and spoiler alert, it's not the moon or the bottom of a frozen lake, came around 1900 thanks to a Danish teacher's technique of attaching marked metal rings to birds' legs and then releasing them. Each recapture or sighting of a banded bird put a dot on the map, and soon long-distance earthly migrations were confirmed when a white stork that had been banded in Hungary was found dead in South Africa. But banding can only tell researchers about single points along a bird's migratory path, not what happens between those points. Researchers finally started to get a better view of these annual migrations when a bald eagle in Maryland was captured and fitted with a transmitter powerful enough to send signals to a pair of orbiting satellites. Satellite tracking revealed details of some remarkable migrations, like the bar-tailed Godwits' annual flight from Alaska to New Zealand, during which the bird covers 11,000 kilometers in about 8 days, without a single stop. But there's a serious limitation to satellite tracking devices. Even with modern technology, transmitters with enough oomph to send signals to satellites are still far too heavy for small songbirds. A slight improvement is to use GPS recorders, which can be smaller because they receive rather than send signals to satellites, but they're still too heavy for the smallest birds. Luckily, scientists have been clever enough to realize they don't need satellite tracking at all. Instead, we can fit birds with a tiny light-level recorder, a clock, and a memory chip, which together weigh as much as a raisin. Lightweight light recorders don't broadcast, so we need to recapture the birds to get the data, but we can then use ancient navigational methods to reconstruct the bird's daily location over the course of its journey. The length of each day is an indicator of latitude, and the time halfway between sunset and sunrise, that is, noon, is an indicator of longitude. These clever geolocators have shed light on the world's speediest migration, the great snipe, which weighs about 170 grams or half a can of soda pop, and hightails it from Sweden to Central Africa in just 3 days, averaging 95 kilometers per hour. Another marathon migrator, the Arctic Tern, has long been credited with the longest migration for its annual round-trip flight between the Arctic and Antarctic, an estimated 40,000 kilometers in total. But recent data from light-level geolocators show that terns actually travel more than twice as far each year, possibly to take advantage of prevailing winds. This means that Arctic terns can rack up over 2.5 million kilometers of flight in a lifetime, enough for 3 round trips to the moon. But as far as we know, they haven't gotten there yet.